Assalamu alaikum شباب. Inshallah today we will continue what we have started last time. So last time we just introduced to thermodynamics, started with the first chapter, introduction to thermodynamics. We have defined here, some vocabularies associated with thermodynamics. We defined some terms like thermodynamic, like energy. We have defined also the conservation of energy principle, and we said it is the same as the first law of thermodynamics applied to a thermodynamic system. And we said for any system, the first law will be energy input to the system minus energy output will equal to the change of energy within the system itself, and it is energy balance equation. Second law of thermodynamics, we said it deals with the quality of energy, not the quantity. So it states that any process has a direction and it has to proceed from the high energy potential to the low energy potential. And we said to study any thermodynamic system, we have two approaches: the classical thermodynamic approach, which gives the average behavior of the system, and this is actually the engineering approach. And we have the statistical thermodynamic, which deals at the molecular level, and we said this one is applied only in some specific application like nuclear reactors. And whenever we have energy transfer or mass transfer, we can have apply thermodynamics in terms of first law of thermodynamics and second law of thermodynamics. We introduced also two dimension and unit. The unit, each quantity has its unit, and we have defined some units of different quantities, and we have seen the relation between how we can convert from the SI system of unit to the English system of unit. We define the property specific weight, which is the weight per unit volume, and we said any property, specific property in this course will be the property per unit mass, except actually the specific weight, it is defined as the property the weight per unit volume. We talk about dimensional homogeneity, and we said if we have equation A plus B equal to C, we said every term in the equation should have the same unit. And this is what is meant by the dimensional homogeneity. Let's continue our talk today. We'll continue our talk today. We'll define actually the different the different systems, the different kind of system in thermodynamics. We said actually in this course, if you recall the course outline, we said we will have the first law of thermodynamics and second law of thermodynamics through this course, and we'll be starting from chapter 4, the application of the first law of thermodynamics for closed system. Chapter 5 will be the application of the first law of thermodynamics for open system. So that means actually we have to define which kind of system we have before we proceed actually solving any engineering problem. In this case, actually, we have two kind of system. Let me just I will start the Zoom video. So we do have two kind of system. We have the closed system and the open system. So let me just show it here. So the systems, we have actually two kind of system. We have the closed system and we have the open system. Closed system is called also, so when you see in any problem, it is called as system. It's called as actually control mass. For control mass, all of this mean actually the system is closed system. So closed system, control mass, all of this means actually the system is a closed system. Open system is called as actually also as control volume. Control volume because the volume in the open system is constant. Control mass for the closed system, that mean actually the mass is constant. So let's consider first the closed system. Mass is constant, that means actually that the differentiation m by dt will equal to 0. Or we can say actually this system, the mass flow rate, m dot inlet or outlet from this system should equal to 0. That means actually this system does not accept mass transfer. So we don't have either mass in or mass out for a closed system. So the closed system is defined as actually as a fixed amount of mass. It does not accept mass transfer. So if you have any system closed system, this system actually does not allow for mass in or mass out is equal to 0. But it allows for what? It allows actually for energy transfer. We can have actually any form of energy transfer. Like what are the forms of energy transfer in or out of the system? The forms of energy transfer, energy can transfer actually by heat. When we have temperature difference between any two systems, then we can have heat transfer based on delta T. Also, energy can transfer in the form of work. Work is defined as actually as the force per unit length. When we have apply a force on a certain body and this body move a certain distance L, so in this case we can say actually this is a work, like a shaft work, like electrical work, we have electronic movement, then in this case we call this also as a work. So energy can transfer by heat, energy can transfer by work when we have a movement of a system, and also energy can transfer due to mass transfer. Like if we have a flow inside a pipe or something, this flow is going with a certain velocity, so it has kinetic energy, and it should be to a reference basis has a potential energy, and also this flow to move, it should have pressure, so we have flow energy also. So we do have different kind of energy transfer due to mass transfer. So those are the three forms of energy transfer. Energy can transfer by heat, by work, or can transfer due to mass transfer. So the closed system does not allow for mass transfer. We don't have mass in or mass out, but it allows actually for energy transfer. And what about the open system? Open system is defined as an arbitrary region, just any arbitrary imaginary region, imaginary boundary, is selected in a given space to do a certain study. Like if I want to study the air inside this room, I will just imagine there is a boundary just around this room, and then we can start studying this room. So this boundary actually is an imaginary boundary, which is called actually as the control surface. We give it actually the abbreviation CS, control surface. And actually this is our control volume, we give it actually CV. So this is actually the control volume or the open system. As this is an arbitrary region or imaginary boundary, so that means actually it allows actually for mass transfer. We may have mass in or mass out. And also it allows actually for energy transfer. We may have actually energy input to the system or energy leaving this system. So the open systems allow for both mass transfer and also for the energy transfer in this case. There is a special case of system which is called actually as isolated system. Isolated system, that means actually this system does not allow either for mass transfer or energy transfer. So it is totally insulated system. The system is totally isolated. So that means actually in this case, mass in or mass out is equal to 0. Also, energy in or energy out is equal to 0. That means the heat transfer is 0, work also is equal to 0. Okay, so the total system is totally insulated. Like if we have air conditioning system, usually we pass the cold air actually from the air handling unit to be distributed among the different rooms in a given building or something. Usually this cold air, while it is flowing inside the duct, is cold and it is surrounded by hot air. So it may be heat up actually while going from the air handling unit until it reaches the required room to cool down. So in this case, we make an insulation around actually this duct. So this insulation prevent actually heat transfer from outside and also prevent mass transfer. So in this case, if we are studying this duct, we can consider it as what? An isolated system. It is totally isolated, does not allow for heat or mass transfer. Okay? But actually inside this isolated system, we may have actually, inside this system itself, we may have open or closed system. So let's say we have inside here, this is system number 1 and system number 2. If I'm studying actually system number 2, I have to define this system, the control volume, if it is an open system, then we can study actually this system, and this system makes it change actually energy and it makes change mass with the next system. So it depends. If you are studying the whole system, this system, the whole insulated system, there is actually nothing to study because actually It does not allow for energy transfer or mass transfer, so we cannot apply the mass equation, and also we cannot apply energy equation because actually there is no any form actually of energy or mass transfer. But if I'm studying this system, then I will draw actually a control volume around this system, control surface, and then I can look at this system, which masses are crossing this surface and which forms of energy are crossing this surface. Then we can apply the mass equation and the energy equation. So we have to define the system first. Before solving any problem, we have to define either this system is closed system or open system. Then we can proceed actually with the solution, because the first law equation will be different, will have different form if the system is closed, other than actually when the system is open. But there is a special case also, which is called actually adiabatic system. So when we say that there is an adiabatic system, adiabatic means that the heat transfer is equal to what? Heat transfer is equal to 0. But actually, adiabatic system can be applied. Adiabatic system can be a closed system and it can be open system. So it does not actually, adiabatic system does not mean actually the system is closed or open. We have to check it. But adiabatic means what? The energy transfer by heat is equal to 0. But we may have energy transfer by work, maybe there. And we may have also what? We may have mass transfer. So the system is open. So either the system can be open or closed, adiabatic system can be open or closed, but the word adiabatic itself means what? That this system does not allow for heat transfer, okay? Time. Let's look here. We can see here actually some example about actually the closed system. Here we have a gas in a piston cylinder device. So the device actually is closed, so we don't have mass transfer, but we may have actually energy transfer. We may add heat here. So in this case, we have the energy transfer by heat. So what will happen to the gas inside? This piston is free to move. Then in this case, the gas will be expanding. So what will happen to the pressure inside this piston cylinder device? Pressure will raise or remain constant. So in this case, actually, as the piston is free to move, then in this case, when you apply heat, the gas will expand and the pressure will remain the same in this case. So for any problem, and this is actually a kind of a trick in your exam, if he said actually the piston is free to move, that means actually the pressure remains what? Remains constant in this case. And this is an example of a closed system. Example of open systems is actually most of the system in our engineering life or engineering application are open system. Like nozzle, like fan, like compressor, like turbine, all of these devices are open system because they allow for mass transfer in this case. We have mass in and mass out. Type, what about the nozzle? This is actually this device, small device. We call it as nozzle. Type, this nozzle, its function is just to accelerate the flow. If I have a flow and I want to accelerate this flow, then we can pass it through a nozzle. The area is reduced in this nozzle in the flow direction. Then the velocity actually of the flow is increased. And as the velocity is increased, the pressure is reduced in this case. Okay? So if this is an example, this system, this device, we call it as nozzle. And the flow in this nozzle is proceeding in this direction. This is nozzle. Because if the flow is reversible, we call the device as diffuser. And the function is totally reversible. So nozzle increase the velocity and reduce the pressure, accelerate the flow. Diffuser will do the reverse. In this case, the velocity, the area will be increasing in the flow direction. So in this case, the velocity will be reduced and the pressure will build up within the system. Because based on Euler equation, delta V equal to minus rho V del V. So we have a negative sign here. So that means actually the pressure is proportional to 1 over velocity. So when the pressure increases, the velocity directly in any situation will be pressure increase, velocity will be reduced in this case. Okay, but we are considering here the nozzle. This is what we are considering here. Consider we have a flow, so that means we have mass transfer. So to study this system, I will just draw this as the control volume. And the surface of this control volume is called as control surface. And look at the masses and the energies that are actually crossing this surface. In this case, we may have heat transfer, heat is lost from the flow to the surrounding. And we have also at the inlet, we have mass flow rate in, and we have mass flow rate out at the exit. Then in this case, we can apply mass and the energy equation. We said energy equation based on the first law of thermodynamic, energy cannot be created or destroyed. So we said energy input minus energy output will equal to the change of energy of the system. The part of energy coming into the system should equal to the part leaving plus the part stored within the system. This is based on the law of mass action that energy cannot be created or destroyed. But we can write it in the rate form, we just differentiate, then we can the rate of energy input minus the rate of energy out will equal to the change of energy dE by dt within this system. And this is actually the form of energy equation we can apply. Inshallah, we'll see inshallah in chapter 4 and chapter 5 how we can apply the first law of thermodynamics. We'll look at actually all of these terms and we'll try to have some application inshallah. Right here we have also mass transfers and we apply mass equation. Mass also is like, mass is like energy. Mass cannot be created or destroyed unless actually based on the Einstein equation that actually energy is equal to half mv squared. Mass can be converted to energy, but when this velocity actually is higher than the speed of light. So this is the only case if a system is moving with the speed of light or higher, then in this case part of the mass can be reduced and can be converted to energy. But actually in normal situation, mass cannot be created or destroyed. So we can say also, like the rate of energy form, we can say rate of mass in minus rate of mass out, m dot out, will equal to dm by dt within the system, the rate of change of mass within the system. So to study any system, open system, we have to draw the control volume, look at the forms of energy transfer to the system and the masses in or out, and then we can apply the energy equation, which is the first law of thermodynamics, and we can apply also the mass equation. And this is an example of an open system. Here is also another example, which is the electric water heater. The idea of the electric water heater here is we have an electric heater. So what electric heater actually provide electric work to the system. Electric work is equal to what? Work dot electric is equal to the volt multiplied by the current. So if we have the current here and we have high resistance coil, the resistance of this coil, heating coil, is very high. So when the current is passing through this coil, then in this case actually this electric work is converted to heat. So this heat can be used actually to heat a cold water. Cold water coming in, then the water will absorb this heat, and then it will be leaving from the top as hot water. So we have cold water in, hot water out, and in this case we have electrical work. To study this system, I will draw also again control volume. This is our control volume, and look at the control surface. What are the masses crossing? We have here in this case, we have mass flow rate in, and we have here actually at the outlet, we have mass out. Then we can apply mass equation. The forms of energy, we have electric work in this case, then we can apply the energy equation to calculate the electric work, okay? And those are some examples for the open system. Open system also like compressor, which is actually used to compress air. Pump and compressor have the same function to compress the fluid, but compressor is dealing with gases, pump is dealing with liquid. Like the pump at your home used to actually raise the pressure of the water so that the water can be raised from the basement floor to another higher floor or something. This is compressor. Turbine, we have different kind of turbine, steam turbine, gas turbine, hydraulic turbine. All of these are turbines. Hydraulic turbine, the nozzle actually is used in the hydraulic turbine system. We have water. Usually we have a kind of dam or something. Okay. Dam, then we have water at high level of water in front of this dam. So at the base, actually, the pressure should be very high. Then we have high pressure flow to this nozzle and to this nozzle to pass through this nozzle. So we have high flow energy here in terms of high pressure. Then we can convert it into kinetic energy, high velocity jet. And then we can have actually a hydraulic turbine with buckets. It's just a blade with buckets. Then this high velocity jet hits the bucket. Then actually this wheel will be driving. Then we can generate shaft power so that we can connect this hydraulic turbine to an electric generator to generate electrical power in this case. And this is the idea of the hydraulic turbine. Compressor is the reverse of the turbine. Turbine actually is converting flow of high pressure, we can convert it to mechanical power. But in case of compressor or pump, we have to have mechanical shaft power. Then we can actually we can increase the pressure of the flow. And this is the idea of compressor and pump. And also another example here for an open system is like when you have a gas in a piston cylinder device, this is actually, but we have an opening here. Opening, that means we have mass transfer, so this system is open. But if it is closed, gas in a piston cylinder device, even if the boundary is moving, so this means actually this is a closed system. But whenever we have an opening, that means we have mass transfer, so the system is open. And this is what we said. We have isolated system, and we have the difference between isolated and adiabatic system. Okay. Types of property to study any system, as we said, let's say the gas inside a room or something we want to study, then we have to draw actually a control volume around the system, and we look at the control surface, which kind of masses are crossing this surface, which kind of energy are crossing this surface. Then we can apply the mass equation and we can apply also the energy equation. But to study actually apply mass or energy equation, we need to calculate the properties. We need to know about the pressure, temperature, density, mass, all of this property we need to know. So property is defined as any characteristic of the system, and we do have two kinds of properties. We have extensive property and intensive property. Intensive property is the properties that actually independent of mass. So it is not function of mass, like pressure, temperature. Extensive property is the pressure that depend on the size of the system, which is function of mass or the size of the system, like mass, the property, mass itself, like the volume of the system, like the total energy of the system. All of these are extensive properties. There is a third kind of properties which is called a specific property. Specific property is the extensive property per unit mass. And the specific properties are one kind actually of intensive property. So all the specific properties are intensive properties. So this is a trick. When it comes to your exam, you see here the definition, specific properties are extensive properties per unit mass. But it is not extensive property. It is extensive property per unit mass. As we divide by mass, so it becomes actually independent of mass. So specific properties are intensive properties. Specific properties are the specific value of any property, which is specific value is the value per unit mass. Specific volume, which is the volume per unit mass. Specific energy is the energy per unit mass. As I told you, any specific property in this course will be just the property per unit mass. Okay. And this is the difference between intensive and extensive properties. Okay. To study also any system, this system has to represent a continuum. Continuum means what? Continuum means actually a homogeneous matter without any holes or any singular point within the system. Like if we want to study this system, a gas in a device, a gas actually in a tank or something, this gas inside the tank should present a continuum or homogeneous matter without hole. Let's say we have inside this tank air. So that means the common concentration of air should be the same everywhere actually within this tank. So homogeneous means we have the same chemical composition everywhere. So air here is about 21% O2 plus, let's say on average 97% N2. So this concentration at the corner should be at the middle, should be actually anywhere. So we can say this is a homogeneous matter. And also without any holes or singular point, we should not have a kind of heat source at a given point. So that means there is a heat source at this point. So this is a singular point. Or we may have vacuum. We have created vacuum, low pressure value at a given point. So this means actually we cannot study actually this point as part of this system. Because actually to calculate the property of any system like the pressure, temperature, we consider the classical thermodynamic. We just consider the average value. Just insert, let's say, a thermocouple at the middle, and I measure the temperature, and this is the temperature value. But if we have a heat source at a given point, the temperature will be different. So we cannot study this system. So to study this system, any system, it has to represent a continuum. It has to represent actually a continuous, homogeneous matter without any holes or singular point. And this is the meaning of a continuum. There is another property also, which is density. Density is mass per volume. We see the specific volume is the volume per unit mass. And density is the mass per volume. That means the density is equal to 1 over a specific volume, or a specific volume is equal to 1 over density. Well, when we talk about density, we have to mention the specific property or a special case property, which is called the specific gravity of fluid. It is a measure of the density of the fluid with respect to the density of water. So specific gravity is the ratio of density of fluid at any condition to the density of water at 4 degrees C. The density of water at 4 degrees C almost it is about 1,000. So you have to keep this value in mind. Here actually in this table you can look at some values of a specific gravity. If the matter is water, so that means it will be density of water over density of water, so the specific gravity will equal to 1. For blood, an example, is about 1 point something. So if we have a volume of a system and mass of the system, then we can calculate the density, and the specific volume is 1 over density. Okay. To study any system also, it has to be at the state of equilibrium. So to study any system, it has to be at the equilibrium state. Equilibrium state is a state of balance. We don't have any kind of gradient force within the system. So that means actually to have a system under equilibrium, it should actually satisfy those 4 conditions. It should be thermal equilibrium. The system undergoes thermal equilibrium. Thermal equilibrium means actually the temperature is the same within the system everywhere within the system, like this example. Okay, but this example here, the temperature is not the same everywhere, so this system is not under thermal equilibrium, but this one is. So thermal equilibrium means actually the temperature is the same everywhere within the system. Like this mechanical equilibrium, pressure should be the same everywhere within the system. Phase equilibrium, that means actually the system is not undergo phase change from one phase to another, like from liquid phase to vapor phase. The system should be at a given state, either liquid phase or vapor phase, or a mixture of liquid plus vapor phase. But we don't have actually any transient condition between liquid phase to the vapor phase, or from the vapor phase to the solid phase through diffusion, or through actually from the solid phase to the liquid phase. This is also a kind of phase change. So we don't have phase change to have equilibrium, and also don't have chemical reaction, because in chemical reaction we have actually the mixture content itself will be totally changed. So if we are burning, let's say, if we are burning a kind of methane, CH4 as an example, with oxygen. So this will need about 2 oxygen molecules to give 1 CO2 plus 2 H2O. So if I'm studying this system before the reaction, so I have a species methane plus oxygen. Now after the reaction, if we have reaction, then in this case, this methane plus oxygen will be converted to totally different species, which are CO2 plus H2O. Then in this case, the properties will be totally different from CH4 plus O2, this mixture. The properties of this mixture will be totally different from the other mixture. So this means actually to have a system under equilibrium, it should satisfy actually that we don't have any chemical reaction. And to have equilibrium of a system, it has to satisfy thermal equilibrium, mechanical equilibrium, phase equilibrium, and also chemical equilibrium. Okay. To study any system, we have to define the state of the system. The state of the system, to define the state of the system, actually we have to have 2 independent and intensive properties. And this is what we call actually as the state postulate. State postulate is the number of required properties to define a state of a system. to define a state of a system, we have to have two independent and intensive properties. What does it mean intensive? Intensive mean actually the property is not function of mass, like pressure, temperature, and all the specific properties, like a specific volume, which is meter cube per kilogram. Type for this system, we have two properties, which are actually independent and intensive properties. Then we can define the state of this nitrogen inside this piston cylinder device with those two properties. And from those two properties, we can calculate all the other properties. Okay? But what does it mean independent? We said two independent and intensive properties. What does it mean independent? Let's give you an example about the independence actually of properties. This example actually is while the phase change process. While the phase change process, actually, I cannot define the state of the system by giving the value of pressure and temperature, because pressure and temperature in this case are not independent. Like water, if we are actually boiling water, converting the water from the liquid phase to the vapor phase, in this case, when we add heat to the water, so its temperature, look at actually at the temperature volume diagram. So when you raise, this is a cold water. When you raise its temperature, add heat up the water, its temperature will be raised. Under atmospheric pressure, it will start boiling at temperature equal to 100 degrees C. Okay? So if I added more heat, then in this case the temperature will not rise. This will be called as latent heat. Then in this case, when you add more heat, just some liquid, this is liquid. The state here of the fluid is liquid. When you add more heat, part of the liquid will be converted to what? To vapor. So at this point we have what? We have mixture in this case of liquid plus vapor. But if I continue added more heat, then in this case all of the liquid will be converted to what? Will be converted to vapor. So at this point we have liquid. At this point we have mixture of liquid plus vapor. At this point we have what? We have vapor. But all of this point from here to here, any point between the initial state to the final state has the same what? Same temperature and also the same pressure, which is the atmospheric pressure. So if I said actually a liquid water, or actually have a mixture of liquid plus water vapor, undergo a phase change process, and this actually the value of pressure is 1 atmosphere, the value of temperature equal to 100 degrees C. So can we specify at which state here we are? We cannot say, because actually all of this point has the same pressure, has the same temperature. So in this case, pressure and temperature are not actually independent. Pressure and temperature are dependent in this case. So in this case, to define a given state, in this case, I have to give either pressure or temperature plus one of the specific property, like a specific volume, specific internal energy, specific enthalpy, any specific property should be given. So one pressure or temperature plus one of the specific properties. Now I know which state I am here. Okay? Then we can define the state of the system. Type process and cycle. Yani this class is a kind of, we have some collection of definition here. Process actually is a change of from one initial state to a final state. We can represent this process on any diagram, like pressure volume diagram, temperature specific volume diagram, any diagram we can represent this process. Okay, like if we are compressing, let's say, a gas from one initial state in a piston cylinder device to a final state. Okay, this actually we call this as a process. And the path is actually the series of states between the initial state as we go actually to the final state. Any point here we call it actually as a state. So the series of states represent actually this process or the path. Quasi-static process or quasi-equilibrium process is the process, actually it is an imaginary process in which actually the process is done actually very, very slowly, so that actually equilibrium is attained everywhere within the system. Like if we have a gas in a piston cylinder device here, if we try to compress actually this gas inside, in this case, while the compression process, we cannot attain equilibrium because the temperature due to friction beside the piston, between the piston and the wall, the temperature here of the gas will be higher than the temperature away. So we don't have thermal equilibrium. Unlike this, also the pressure will not be the same everywhere. So in this case, the process cannot be at equilibrium, while any process actually we cannot attain equilibrium. But this is actually a kind of an imaginary process or a reversible process in which we assume actually this process is done very, very slowly so that actually equilibrium is attained everywhere. Pressure of the gas is the same everywhere. Temperature is the same everywhere. Then in this case, actually, we call this process as quasi-static or quasi-equilibrium process. Very slow process in which actually equilibrium is attained everywhere within the system. Here is an example of this process if we are compressing a gas from initial state 1 to a state 2. So in this case, what happened to the volume? Compressing, that means the volume has been reduced. V2 is less than V1. What happened to the pressure? In this case, we are compressing a gas, so the pressure has been raised. And as the pressure increases, the temperature also will be increasing. So we can present those processes on the PV diagram from state number 1. Pressure will be increased and volume will be decreased. And we can just draw this curve from initial state 1 to a final state 2. This is a kind of general process, but there are actually a special kind of processes which are called actually the isoprocesses. Isoprocesses which are actually processes of constant, one of the parameters is constant. Like when we have isothermal process. Isothermal process mean actually, iso means equal. So isothermal means actually the temperature actually is constant. We have also another kind of process which is isobaric. Isobaric means the pressure is constant. Isochoric, the volume is constant. Isentropic means actually the entropy of the system, fluid inside the system is constant. So special processes. We have first of all isothermal process. Isothermal means the temperature through this process is constant, or the temperature at the initial state, T1, is the same as T2. We can represent this process on, let's say, on the temperature, a specific volume diagram. A specific volume is in meter cube per kilogram, and temperature in Kelvin, okay? As it is actually isothermal, temperature is constant, so it can be either actually from state 1 to state 2. It will be just a horizontal line on the temperature volume diagram. We have another kind of process which is called isobaric. Isobaric process in which actually the pressure should be constant. We can represent this on the PV diagram, pressure specific volume, also by a horizontal line either from state 1 to 2 or from 2 to 1. We have isochoric process. Please keep those processes in mind. It comes to your problem. Give you, this is actually isochoric means the volume, the specific volume is constant. So let's say on the pressure volume diagram, volume is constant. So it will be a vertical line either from state 1 to 2 or from 2 to 1. Another process, which is the isentropic process. Isentropic process means actually the entropy is constant. Entropy is a property calculated in kilojoule or joule per kilogram Kelvin. It is a measure of randomness of molecule, random motion of molecules, and it gives us indication about the amount of energy in kilojoules that is dissipated due to the random motion of the molecules. So while the molecules are moving, they dissipate actually kinetic energy, and this amount of energy dissipated, kinetic energy dissipated, can be represented by the property which is the entropy. Okay, if the entropy is constant, then in this case, we can represent it on the temperature, let's say entropy diagram. Entropy is constant, so it will be a vertical line from state 1 to 2 or from 2 to 1 in this case, okay? If we have isentropic process, as we said, if we have a system, undergo an isentropic process, so entropy will be constant. So this is a system. But if we added heat, so the activity of the molecule will be increased. It will absorb part of this heat, then the entropy will not be constant. So to have entropy constant, so this heat transfer should equal to what? 0. But if we have friction within the system, friction at the end will be converted to heat. and then the entropy will be increased. Then in this case, this system should be what? Should be frictionless, or friction is equal to 0. Okay, so to have an isentropic process, entropy is constant, the friction should be the system should be adiabatic. Q is equal to 0, meaning the system is adiabatic, and also the system should be without friction. And this is an imaginary process. This is what I want to say here. If we have a system undergo an isentropic process, this system should be adiabatic, and this system should be without friction, which does not represent the real case. So isentropic process is an imaginary process in which we assume the system is adiabatic and frictionless. What is the difference between process and cycle? Cycle actually is a series of processes. Cycle is a series of processes starting from one point and then ending at the same point. On the PV diagram, if we are representing a cycle, it is a series of processes. Let's say process from 1 to 2 at constant pressure, isobaric, and then we have another process from 2 to 3, isochoric, let's say, and another isobaric process from 3 to 4, and the final isochoric process from 4 to 1. Now we started from this point 1, do series of processes and getting back at the same point. So in this case, we call this system as what? A cycle. And any actually engine to provide continuous or generate continuous work, it has to work on a cycle. Because working on a process, it will just do the process and it will stop. So for any system to generate continuous work, it has to work on a cycle. Starting from one point, doing series of processes and getting back to the same point. And in this case, the change of energy of the system will equal to what? Change of energy of this system will equal to the final energy final, minus energy initial. But the final point is the same as the initial point. So that means the change of energy within this system, change of energy of the system working on a cycle, this change of energy should equal to 0, because it is equal to the final energy, E final, minus the initial energy initial, and we have the final point is the same as the initial point. So in this case, we can say the change of energy for a system working on a cycle will be equal to 0. Okay. I will not extend it much, just I will end up with this topic, which is the steady flow process. I think you know about steady process. A steady process means actually we don't have a change with time. So d by dt within the system, change of any property within the system with time is equal to 0. This is the meaning actually of a steady flow process. I give example, so steady flow. Example of steady flow. Just let's say we have here this tank. We have some flow is getting in, mass flow rate in. Some flow rate is giving out, mass flow rate out. And let's say also we have any form of energy in and any form actually of energy out. Rate of energy in, E dot in, and energy out. So as we have mass transfers also, this system is an open system. So we have to draw a control volume before solving the problem, and look at the control surface, and look at what kind actually of mass is crossing this control surface and what forms of energy are crossing. Then we can apply mass and the energy equation. Applying mass equation, it will be m dot in minus m dot out will equal to rate of exchange of mass dm by dt within this system. We said actually for a steady process, steady means actually the change of any property d by dt with time within this system should equal to 0. This is the meaning of a steady process. Steady process means we don't have a change with time within the system. If we have a steady flow here, so the pressure here at this point and the pressure at this point, it does not change with time, but it can change with location. So we may have, let's say, the temperature here is equal to 300, temperature here is 320, but actually this 300 does not change with time. So from time to time, the temperature here is the same at the same point. but it can differ from one location to another within the system. So steady flow means we don't have a change of property with time, but it can change from one location to another location. Type, this is a mass equation, dm by dt. If this system is a steady flow, then in this case we don't have a change of mass with time. Then in this case it will be dm by dt, in this case will equal to 0, and that means actually the rate of mass flow rate into the system should equal to the rate of mass flow rate out of this system. This is actually the meaning of a steady flow. So if we have a steady flow, that means the mass flow rate in should be the same as mass flow rate out. Like this also we can apply energy equation, energy dot in minus energy dot out will equal to dE by dt within the system. d by dt will equal to 0 in case of a steady flow. Then in this case we can say actually the rate of energy in to the system will equal to the same as the rate of energy out of this system. Energy dot in is equal to the same as energy out. But that means actually for a steady flow, as energy input, mass input is the same as mass out. So that means the mass of the system itself is what? Remain constant. Mass input is the same as mass out. So the mass of the control volume will equal to what? Will equal to constant. So for a steady flow process, the mass of the system or the mass of the control volume will remain constant. Like this also, energy input is the same as energy output. So that means the energy of the system itself will remain constant. So this means the energy of the control volume or the system will remain constant if we have a steady flow process. Okay, so steady flow means actually we don't have a change of time. Okay. So inshallah next time we'll end up with this chapter. We'll talk about the temperature scale, Celsius scale, Kelvin scale, Rankine, and how we can measure the temperature, and also we'll talk about the pressure scales, gauge pressure, absolute pressure, and also we'll talk how we can actually measure the pressure, including actually the atmospheric pressure. Okay, so let's end up at this point inshallah, and inshallah we'll continue next time. Assalamu alaikum.